Hi, everybody. Welcome back to the Schuko Statistics Lecturing Series. And we're still in this unit, Introduction of Probability. And we are currently, right now, this video will cover the lecture number 5 here. We're going to have 2 videos to cover the lecture number 5. So in this lecture number 5, and the first part of the video, we're going to talk about the probability postulates, the theory, and the rules. And then the second video, we're going to focus on talk about the addition rules for the, if you have units of the two events here. And so let's see here. So for the first video, we're going to talk about a lot of the postulate and the theories associated with the probability rules. And then the one I highlighted in the red, those are, we call these the addition rules. We're going to cover these two at the video number 2 because those are very, very important rules here. Then for the video number 1, we're going to end the video number 1 with 3 practice examples. Then we'll continue, go to the video number 2, we talk about the addition rules, and then we have another 4 examples on the video number 2 here. Okay, so now let's go ahead to start to see what are the postulates and what are the theories here. Okay, I'm going to the whiteboard right now. Okay. Okay, so let's start here. So the first thing is here we are going to talk about is the postulates. And this is just mathematical terms. So people say, what is the postulates, right? So postulates really, it's kind of like the theory, but we don't need to prove it. It's kind of, we accept it as a fact. It's what we claim, right? So the postulate. So for the probability postulate, we have 3 basic postulates and have to satisfy in order to be, we say this is probability measures here. Also when we go through all these theories here, you'll find out a lot of those theories are kind of a common sense, and so that's why I think, if you understand that, and it's kind of common sense, it's not too complicated. Okay, so the postulate, the first postulate for the probability measures here is number 1 here. That means we say, hey, whatever the events inside, right? So the probability of every event has to be greater than or equal to 0. So you need to remember this. So like later, all the later lectures, when we talk about the probability, if you figure out some probability, if you get a negative number, then you know this is not correct because the probability has to be positive or zeros here. All right, so this is what we call this a postulate number 1. Okay, so now let's take a look at postulate number 2 here. This is also common sense. So we say the probability, if you take a look at the whole sample space, right? So probability of the S is here. So this one has to be equal to 1 here. That's kind of common sense also. Let me see, if you include all the outcomes of the experiment, that is 100%. And we use this postulate a lot later when we do the probability calculations here, because we said if you include all the elements in the sample space have to be 1 here, right? Okay, so then the postulate number 3 is here. Okay, so this is one also is kind of like the very intuitively true. So let's say here is like if you have events here, okay, A1, A2, and A3, and does not matter, right? This is finite or infinite events, right, in the sample space. Remember, like our previous sections here, we talk about the sample space. You can have finite outcomes, or okay, you can infinity outcome. So the events is the same. If those are the events in the sample space, and if they are And also if they are, it's only not only the events here, they are also what? They are the, we call this the mutually exclusive. Remember that definition? So the mutually exclusive, that means all these events, they are disjoint. So for example, this is A1, this is A2, this is A3, this is A4, right? So this is A1, A2, A3, A4. So they are all disjoint, right? So that's why we call it mutually exclusive. And then the postulate number 3 tell you, see here, said, hey, if they are mutually exclusive, then when you union them together, so this is A1 union A2 union A3, see here, and there will just be probability what is A1 plus probability of A2 plus probability of A3 and That's what we talk about, right? So because when you unions here, basically you just combine this one, this one, this one, this ones, right? Because they are mutually exclusive, so when you union them, it's just equal to you are adding them together. So those are what we call this postulate. We take it for granted, and this is what we claim, right? So it's not a proof associate, right? Okay, so the theory, that means you can prove it. And in here, I'm not going to prove the theories here. I'm just want to talk through that. So like I said, most of those things are kind of like common sense here. But of course, if you want to be very, very like mathematically to prove it, you can do it. But that's not the focus for this lecture series here. Okay, so the theory number 1, they tell you, they say if A is an event, is a discrete sample space, then PA, the probability of A equal to the sum of the probability of each outcome comprising the event A. That means event A, so here, this is a key word here, we need to be careful, right? So that means if the event A is a discrete sample space, then for example, if event A has like the like have 3 outcomes or 4 outcomes of your events, then the probability of the A will just be you add those each outcome because of they are discrete, right? So those outcomes, right, they are kind of the separate, right? So it's disjoint. So you can add each individual outcomes here. Okay, so let's take a look at that. So it's kind of like it makes sense. So if the event, so let's for examples here, if the event A, I have a like an outcome like a OPRS, right? So I have 4 outcomes. So OPRS, become event A, then the probability of A will just find, so you will figure out what is the probabilities, right, for each outcome. So this outcome has a P1, this outcome has a P2, this outcome has a P3, this outcome has a P4 here, right? So the probability of the A's here, right? So probability of the A's here will just be you add those each individual outcome. And of course, here is only true if it's from the discrete. Okay, let's take a look at theory number 2 here. This one is also is kind of like the very kind of the common sense. Let's take a look at what is the keyword. So let's say if the experiment result in any of the n, so the like your sample space, this is the total number of the sample space, right? And the different equally likely outcomes. So this is a very important thing here. That means in your sample space, every outcome is equally likely. Then if the event A composed of the n outcome, then the probability of the A is just equal to the little n over capital N here. So this one is easy to understand here. So for example, right, if I toss a die, right, so the sample space, if I toss a balanced die, okay, I should say I toss a balanced die, that means equal. So that means the sample space is 1, 2, 3, 4, 5, 6, right? All right, and because this is a balanced line, that means each element in the sample space have an equal chance to happen. Now, if I define the event A, if I say event A is get an R number, right? So now the A will be what? A will be 1, 3, 5. So based on this definition, then I know the probability of the A is 3/6. But we need to be careful. That means with under the equally likely outcomes, right? If it's not, then it's not true. If it's not equally likely, then you need to go back to what? Go back to the theory number 2 here, right? To see what is the, the event A is the outcome, the make up the event A, then what are the probability for each outcomes here. All right. Okay, so theory number 3 is also, this is, I think, is a pretty obvious theory. They say if A and the A prime are complements, right? Then the PA prime is equal to the PA. So this one is easy to understand also, right? So this is so the things here, okay, so this is S, right? We said a Venn diagram showing like, so the Venn diagram showing the, the sample space. So here I have events A here, right? So the events A, right? So the events A is here. So the probability of events A is this, what is this purple area over the sample space, right? Okay, now the A prime, you still remember from our previous video, what is A prime? A prime is what? Hey, it's everything outside A, right? So this is A prime here. So this is A prime. So the probability of A prime is all this green outcome over the sample size. So, and I know the sample size is 1, so that's why it's 1 minus PA, right? So if the A is like the, so for examples here, like for the second example, if A is odd number, then PA prime is the probability of even number. So it's 1 minus 1/2 here. Okay, so now the next thing here is this one is kind of like also is a trivial here. So what is this symbols here? This symbol means empty set. Okay, so the probability of an empty set, that means I don't have anything, right? So it's obvious it's zeros, right? So probability for nothing here, the empty set is 0. Okay, so that's kind of opposite to the probability of the whole sample space, right? Whole sample space is 1, and probability of an empty set is equal to 0. Okay, so the theory number 5 also is pretty straightforward. So let's say if A and B are the event in the sample space. So what does this symbol mean? This symbol means sometimes you can say this is belong to, or some people they say it's inside. Okay, so in here, this is kind of trivial also, right? So let's take a look here. Okay, so in here, you have a sample space here. Okay, so this is my sample space here, right? So now I have events B here. The green is my events B, right? So now A is inside B. That means let's put the A is here. A is here, right? So this is A, right? So the probability of A is this yellow area, right? And then probability of the B is what? The B is this green area, right? So obviously, so probability of the A is less than or equal to probability of the B. So like I said, all these 5 theorems are very kind of intuitively, and it's kind of like a lot of common sense, but they are playing a very, very important roles in the probability rules, okay? So now let's take a look. So those are the 3 problems we're going to practice. So now if you want, you can pause the video and based on the lectures, and you'll try to do these 3 problems to see you'll be able to figure that out And afterward, then you can resume the video, and then we can work those problems together. All right, and then you can check your answer. So that would be a pretty good way. You can see how much you understand the lecture and how much you can go with those problems here. Okay, so if you want to pause your video, and you can pause your video and then try to practice it by yourself. Okay, so let's try to work it. Okay, let's start. I hope you do have, you did have chance to practice some of those problems before you look at the video, and that will be a good way to learn, because you kind of look the problem and tried, and now we can check the answer, right? Okay, so now the problem number 1 is here. They say a die is loaded. Okay, so it's not a balanced die. It's a loaded die. So how is this die is loaded? So in such way, they say the odd number is twice as likely occurred as even numbers here. So I'm going to find the PG. So what is the G's here? G is you get is the event. Number is greater than 3. Okay, so when you do those type of probability problems, the first thing is you will write it. You say, okay, so let's see what is my sample space. That's right. My sample space here, when you roll the die, you have 1, 2, 3, 4, 5, 6, right? And the G is the events you want to find. So in here, the G is you will get an event is greater than 3. So the event G, this is 4, 5, 6. Right? Okay, so let's what okay, I got it back. I thought I erased it. That's not good, right? Okay, so now let's take a look here. So, if this die is a balanced die, like we did before, right? If it's a balanced die, right? That means each number have an equal chance to happen here. So let's put it here. So let's say that here. So if it's a balance, if it is a balanced die, then the PG, very easy. What is here? 3/6, right? So it's a little n, lowercase n over capital case N, right? But in here, unfortunately, so this is not true because the die is not balanced, it's loaded. So in here, they said it's loaded. Odd number is twice happen as even number. So how do I solve these problems here? So I will say here, all right? So I will say, okay, that, okay, so let's start here. I said W, okay? This one's here, let's say this one is the probability. This is a probability to get a even number. Okay, and because it's loaded, so odd number has twice. So I have a 2W is the odd number. Right? So 2W is the probability of the odd number. Now I'm going to use the postulate number 2. When you add all the sample space, what is here? So take a look. This is very important. So when the sample space, you add all the sample space, has to be ones, right? Okay. So I know the odd number is 2, right? 2W. So I have a 2W plus W plus 2W plus W plus 2W plus W is equal to what? Equal to 1, right? So what is here? This is you will get 1. This is you get 2, right? This is you get 3. This is you get 4. This is you get 5. This is you get 6, right? Because it's loaded, then I use the postulate number 2. The whole sample space is equal to 1. So now I can solve it. And now I will say what is here. I will have is 9W is equal to 1. So I get my W. W is what? W is the probability 1 over 9 here, right? Now I'm going to find the probability of G's here. Because G is composed of the 4, 5, 6, so the probability of the G we're going to be 1 over 9. Now it's an odd number. It's 2 over 9 plus 1 over 9. So what is here? This is 4 over 9 here, right? So what theory I was using? I was using theory number 1 here, right? So this one's here, right? So be careful here. And this one I using what? This one's here, I use a postulate, PS equal to 1, right? And this one's here, I use what? Theory number 1, right? So if you if the event A has the composed of the different outcome, then you just add the probability of these outcomes here. Okay, so now in here, I said for experiment, okay? And so for this experiment here, I have these outcomes here. So O1, O2, O3, and this is infinity sequence of the outcome. That means when I do this experiment, I have this, I have this, the outcomes is O1, O2, and this outcome to the infinity. And the probability of each one is 1/2 to the i's power. So that means, so what that means here? That means the probability of the outcome number 1 is equal to 1/2, right? And the probability of the outcome number 2, this is equal to what? 1/2 to the what? Squares, right? Then probability of the O3, that means it's 1/2 to the third, right? And da, 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 da. Okay, so now they said that, hey, if this is a probability measures here, so if it's satisfied the probability measures here, we have to know, that means each one is greater than 0, right? So we said, okay, so POI, that's no problem. This is greater than 0, right? So I cannot have a probability, it's a negative probability. Then the next postulate we said, the next postulate we said with, the probability of the S's here has to be equal to 1. That means if you add all the outcomes, it has to be equal to 1 here. Okay, so now let's take a look. How do I add all the outcomes? So that means I have O1, O2, O3. So probability of the whole sample space, right? So it will be the PO1 plus PO2 plus PO3 and plus da 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 da. And then this one's here will give you 1/2. Then this one will give you 1/2 to the square. This one will give you 1/2 to the third. And da 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 da. And so, how do I show this is 1? Okay, so let's take a look. If you take the 1/2 out, so this will be 1/2, 1 plus 1/2 plus 1/2 to the square plus 1/2 to the cube, da 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 da. Right? So then you notice it. You say, oh, what happened to the things inside the bracket? This one, they change the ratio is 1/2, right? So this is here, ratio is 1/2. This is what? Ratio is 1/2. So I know inside this is what you learn from your calculus class. What do we call this? This is a geometric series, correct? This is a geometric series with R equal to what? R equal to 1/2. So do you still remember how do we find the geometric series? So here we say the sum of a geometric is equal to 1 over 1 minus r. Correct? That's what we learned from our calculus. So now I can use that sign. So this is 1/2, right? Okay, times 1 over 1 minus r. So it's 1 minus 1/2. So if you put, you calculate that, it's get 1. All right, so that's why I know this is a correct probability measures. So I can define this as a sample space, because when you add all the sample space together, and then it has to be equal to 1. So this is, we still use the postulate, right? So that's we need to verify. Like I said, the probability of a sample space equal to 1 is very important postulate, because we use it a lot. All right, so let's take a look at number 3. So for the people like to play the poker, this will be interesting. You can figure out what is the chance, okay? So let's say a 5-card poker hands, and from 52 cards. So we said if this is a full house, okay? If it's a full house, that means you're going to have a 3 of a kind and a pair. All right, so 3 of a kind. So if you get a jack, so you need to have a jack, 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 right? 3 of a kind. Or if you got a 6, you need to have a 6, 6, 6. Then go to get a different pairs here. Okay, so if all the 5-card hands are all equal likely, okay, so the key word here are equal likelies here. So now I want to find the probability. What is the chance I'm going to get a full house? So for this problems here, I'm going to use the, the probability of the A is equal to n over n's, right? So lowercase n over uppercase n's here. So because the every hand is equal likely, so the first here, so I want to find here, this is the full house. This is kind of like we need to use the technique, go back to what are our previous videos about the counting rules, right? So we need to know how many in the sample space. That's why we went through the counting rules, okay? Okay, so now let's see here. Every time, right, you dealt with 5 cards, with 52. So total, how many ways? Remember the counting rules is 52, take what? Take 5, right? Because this is a combination, I don't care which card I got the first, which card I got the second, as long as I got the 5 cards, right? So this is 52 times 5. Okay, so now I want to have a 3 of a kind, right? 3 of a kind. So a set of a card, a deck of card, we have 13 different kinds from S, 2, 3, 4, all the way to the kings, right? So we have a 3 of a kind. So that means the first one's here, out of this one, I need to choose one. So I have 13 different chances, correct? So I can choose S, I can choose 1, I can choose 2, I can choose 3. So I have a 13 different way to pick out one. I'm going to have a 3 of a kind. Okay, so whatever the one you pick it out, because each kind have 4 cards, right? Because we have 4 suits here. So that means this is then out of the 4, you take 3 of them, right? So after you decide the 3 of a kind, for example, if you pick 9, now I need a pair, right? So after you pick out 9, how many left here? You have 12 cards, 12 different kinds left. Am I right? All right. So you have 12 different kinds of cards left. So you need to pick another kind. And for these ones here, because it's only require a pair, so if you pick a queen, so how many situations is 4 out of what? 4 out of the 2. Okay, so let's try to review. So what is the top rules we use? We use the multiplication rule, like when we talk about the counting rules, right? And the bottom, this is what we call it combinations, right? Okay, so that what is the probability I'm going to get a full house. So if you like, you can put this into the calculator, and then I already did it, so the chance is 0.0014 here. Okay, so it's only 0.1% of the chance to get a full house. All right, so that's the end of this video. So here, I hope you got, when you did it by yourself, these 3 problems, I hope you got most of them correctly. And so that's it. And our next video, we're going to focus on talk about the addition rules here, right? So how do I find the addition rule to apply to the probability of events here? Okay, that's it. It's very nice to talk to you. If you like the video, and you can subscribe it. And also, if something still confuses you, leave me a comment, and I will answer your questions here. Okay, so it's nice to talk to you, and then I think I'm so looking forward to go to the second part of this video, and we talk about, when we talk about the sorry, see, I got so when we talk about addition rules here. All right, so that's it, and talk to you later. Okay, bye.